Good afternoon. My name is Franz Hutchinson, and I'm from the UK side of the Inflector worldwide, if you like, group. And we're dealing with the expansion throughout the whole of Asia at the moment. And of course, Chris and Elke have got Inflector Asia up and running. And this is the first launch of the product, where everybody will be able to see for the first time, really, exactly what we're talking about. And some of you have already had a little bit of an insight from Chris and Elke because you know them. But I want to show you something here on a demonstration side. So I don't want to take too much of your time because I know that you want to get away after you have had your lunch. So I'm going to go straight into the demonstration. What it is, we've got a brand new type of window insulator. And the insulator is it's a see-through radiant barrier. It was designed by NASA for space travel, so that when they're out in space, the heat of the sun, because it's quite strong out there, there's nothing to stop it coming through the windows, and they had to be able to see through there as well. So now we have now developed it for a window insulator. It does exactly the same thing. But it does a lot more than that, and I'd like to show you that as well. But what I have here is a demonstration of exactly how the Inflector works. If you go back a little bit to your days of science, energy flows through a thing by convection, conduction, and radiation. I don't want to go too deep because I know I can get boring with all that. But anyway, convection, conduction, and radiation. Convection and conduction is what the window industry has been dealing with for such a long time. In other words, they're going to have double glazing, you're going to have the frames are going to be beefed up, you're going to have more insulation in the frames. Conduction is the actual start of it all, i.e. the hot, in this area it's outside heat coming into the building. In my area it's mainly inside heat going out. So I'm having to twist things around in my head a little bit to give it you on your side. So in other words, if we've got cold air in here and we've got hot air out there, then it'll transfer through that window very easily, because this is a single pane window in here. So it's the worst case scenario, and I'm going to show you exactly what I mean by that. But convection and conduction is only 25% of your heat loss through a window. Radiation, which is all heat is radiation, and radiation is at the speed of light, so anything that is see-through, radiant heat will go through it, okay? So that's the massive difference between what you're used to with regards to windows and what I'm going to actually show you today. So I've got a little experiment here, and I would love if one of my assistants over here can come and, because I need somebody to read this meter. Okay. What I've got here is I've got a radiant heat. It could be any source whatsoever. In this particular case, it's an infrared heat lamp. Okay? On this side, I have a meter which measures BTUs. But it's quite a nifty little meter, because when I switch it on, let it warm up a bit, I can actually put it into percentage. So if there's nothing in the way, 100% of the heat is hitting the sensor, so therefore 100%. If we put something translucent in the way, i.e. glass, it drops it down to 83%. Okay, so 83% of the heat is still coming through the glass, because radiant heat will go through something that's see-through. Double glazing, a lot of people obviously have double glazing around here. I don't see very much actually, but not in Hong Kong. Anyway, double glazing is two panes of glass with all sorts of things like gas in the middle or just ordinary air. If I put that into the equation, it drops it down to 67% of the heat is still going through the double glazing. We have a glass in the industry called low-E glass, which is what you'll probably find in most of the buildings around here. It has a film inside this, which is attached to the actual glass itself, and it stops radiant heat. And this is what the industry have given us. And the radiant heat that it stops still allows 58% of the heat to still go through the low-E glass, okay? So if we go back to the worst case scenario, which is like this here, which is single glass, can I just hold that a second? So 82% of the heat is still coming through, and then we introduce the see-through radiant barrier into the equation, and it drops it down to 18. So in other words, one piece of glass and the Inflector stops 80% of the heat traveling through the glass. It's a massive difference. The inflector itself, on its own, will stop 22. Can you hold that a second? But people always say to me, you know, what about triple glazing and quadruple glazing, whatever? If I put 5 panes of glass in the way, take that out a second, and it stops 33% of the heat. So in other words, 5 panes of glass, and that's one of those with the low E, and 2 air gaps only stops 34, it allows 34% of the heat through. So in other words, 1 pane of glass and the inflector stops 80% of the heat going through. It's a massive difference to everything that's going on here. Now, the inflector, I'll turn that off because I'm starting to heat up. Sorry about that, thank you. The inflector has 2 sides to it. I know that Hong Kong, most of the year, is going to be around about 33, 35 degrees, something like that. However, you're just about to have a bit of a shock because within the next month, your temperature is apparently going to be reduced down to 10 degrees. So in the summer months, what we do is we have 2 sides, the summer side of the inflector and the winter side of the inflector. In the summer months, we want to keep the heat out of the building. So we turn the inflector into this side, which is the rejection mode. So solar rejection mode is the silver side pointing out. It actually, when you've actually got it on the window, it becomes a one-way system. You can't see in. So when you can see out, but you can't see in, so that's what happens. But what it's doing is, it's reflecting the heat of the sun back out through the window. It's stopping it coming through. But from the inside of the building, you can still see through it. This particular version on the top here is the Energy Saving Truss, which is in Scotland. And that is the inflector on the window in a vertical blind mode. And it's actually solar rejection. It's stopping the heat from coming through the window. In the winter, when you get those massive drops in temperature, you turn it round. And this product becomes a solar passive heating panel. So it brings heat from the sun into the room at approximately 600 watts, as long as the sun is on the panel. It brings in 600 watts per meter squared. So you've got hot windows. You can heat a building with this particular product on a sunny day. It can be minus 10 or 20 outside, but inside the building you can have a lot of heat coming through from the passive solar panel. So it's got a good response to heat rejection and heat infiltration for this particular thing. In Hong Kong, one of your main problems is that you have a lot of humid air outside the building, okay? So at this moment in time, in here we've got air conditioning, which is trying its best to get rid of the humid air that's in this room. And it comes out in condensation, as you know, from the machines that's dripping all over Hong Kong. What you need to do is you need to stop that air from outside getting into your building. Now, at this moment in time, those windows are very hot. This air in here is cold. So consequently, when it touches, the cold air in here touches that warm air there, what happens is it heats up. When it heats up, it rises and forms what's called a thermal loop. So in all your buildings, this loop starts to move. Now you mask it by putting cold air into the room to stop this from carrying on, stop it from coming off. If you touch those windows whenever, you'll find them quite warm to the touch because radiant heat is hitting that and it's actually making those windows quite hot. So your thermal loop starts to go round inside the building. What it does is, if they're old windows and the seals are not very good, it drags the air from outside and puts it inside your building. So you've got moist air inside the building. You've tried to get rid of it by the air conditioning and it's dripping out. You're bringing more moist air in. It's called infiltration. And infiltration is stopped by the inflector. We can actually stop this because what it does is it creates a barrier between the window itself, which can be 35, 40 degrees. In fact, in Chris's office the other day, we measured 44 degrees on the heat of the window. The back of the inflector, when it was in position, was 15 degrees lower than that. Okay? So it's down to 27 degrees. So in other words, we've got a situation here where the cold air isn't touching the hot windows anymore. It stops that. So it stops the infiltration from the outside. So not only do you get the fact that you're reducing the amount of air conditioning that you're using quite significantly by just putting this in the window, but it also stops the infiltrated air coming in as well, which can add another 6% to the cost of cooling this air down in here, because wet air costs a lot more money to cool than dry air. So we've got that as well. In here, it's the appliance of science really, because in here there's 3 layers. You've got aluminium on the front face, you've got carbon graphite on the back, and that is punctured, so therefore you can see through it. As you can see here, we've got it on the windows there, and we've also got it here. And that's the sort of view that you get through the window when it's on a vertical blind. That's closed, by the way. The blinds are closed in that position. But also in this, we have a UV barrier, so it stops UV light and heat coming through the window. 92% of the UV, so it doesn't damage your curtains, your fabrics, your chairs, your pictures, all this sort of thing. 92% of the actual UV is also stopped. So from a little bit of material, it does quite a lot of things. It gives you the rejection of the solar gain, it brings in heat when you need it, it stops the infiltration because it's impermeable. In other words, the actual air from inside the building can't mix with the window. That's very useful, especially when it goes cold, because in the cold position, which means that the silver side would be in, you end up with another layer of air between the window and the room air. So they don't actually intermingle. So therefore, you get more convection and conduction from this as well. So not only is it a radiant heat barrier, but it also increases the amount of convection and conduction that your windows can produce. You can use it as a blind. The one that's on this picture that you can see behind me here is a vertical blind. This is the best way of putting it in the window, because if I want to turn it round, I just swivel the mechanism. So I can have it on solar rejection, bring it in, open the window completely if I want to have a bit more light, because it does affect the way that the light in the room is, because it's doing a specific job. As I remember I said that it's at the speed of light that this is happening, so when it is on the window, it does affect it. It looks like this. This isn't doctored, this picture. This is exactly as it looks on the window. So quite literally, if you said, well, today I just want more light in, you would just withdraw it to one side. So it's flexible. It has a complete flexibility. This is it in an actual roller blind. We've done a few of these. We've actually done one of these over in the Visa building in London. We've done a whole section of their building. And twice a year, once in the winter and once in the summer, somebody is paid to come along and just switch them round. And they just unhook them, turn them round so they're in winter or summer mode. And they can turn it on, they can turn it off, as simple as just pulling the cord. So it's quite an easy thing to do. It reduces glare by about 80% as well, by the way. So in other words, when you're looking out of the window, like today, it's not that bright. But if the sun was out, it would be quite bright over there, and that would be very glary. It would cut that down by 80%, which is quite handy. Thank you very much.